Hello everyone, welcome back. Today we'll see resistors. So we'll just recap the last session. In the last session, Unit 1 Lecture 2, we have seen AMBA technology, that is Advanced Advanced Microcontroller Bus Architecture Bus Protocol. So, and we have seen the AHB's two versions, that is multi-layer AHB and AHB Lite. We have also seen embedded system software, different layers. We also studied ARM core data flow model. And now today we will see resistors. This ARM system has total 16 resistors here, each of 32-bit wide, and there are up to 18 active resistors. 16 data register and 2 processor status registers. So you can see on a diagram. So there are R0 to R15, total 16 registers are there. And R13 has a special property, so that is dedicated to SP, that is stack pointer. So why is that stack pointer? So stack pointer stores the head of the stack in the current processor mode. Next we have R14 link register. The purpose of this link register is to put the return address whenever it calls a subroutine. Whenever subroutine has been called, then the return address is saved in a link register, that is register number 14, R14. Next we have a R15 PC. This PC is nothing but a program counter. It contains the address of the next instruction to be fetched by the processor. And we have seen here 2 processor status register. Here it is only given the CPSR because the register given here are the user mode registers. So when our ARM is operating in a user mode, in that mode we have got only CPSR. In other modes we have one more register called SPSR. So SPSR, what is the meaning of SPSR? Saved program status register. Saved program status register. So this SPSR will be significant in other modes. It will not have any significance in a user mode. We'll move to next slide. And in ARM state, the registers R0 to R13 are called as orthogonal. What is orthogonal? The orthogonal means any instruction that you can apply to R0, that you can also equally apply to other registers. So if any rules apply to R0, that is equally applied to R13. And there are instructions that treat R14 and R15 in a special way. So that means only R0 to R13 registers are orthogonal, not R14 and R15. Next we have, in addition to the 16 data register, there are 2 program status register, as I already told you, that is CPSR and SPSR. CPSR means current program status register and SPSR means saved program status register respectively. Next we have current program status register. You can see on a screen the CPSR register. As the ARM is a 32-bit register, the CPSR is also a 32-bit register. You see here from bit 0 to bit 31, isn't it? You can see bit 0 to bit 31. The ARM core uses the CPSR to monitor and control internal operations. The CPSR is dedicated 32-bit register and resides in the register file. So you can see on a screen. The CPSR is divided into 4 fields basically. So each is 8-bit wider. You can see in the diagram. So flag like from 0 from LSB here to here, total 8 bit, 0 to 7 bit. Fine. Again from here to here, again 8 bit. From here to here, status 8 bit, and from here to here, flag section, that is also 8 bit wide. So this 32 bit wide is divided into 4 sections here as flags, status, extension, and control. So in the conditional flag, we have flag fields. In control field, it contains the processor mode, state and interrupt mask bits, and left status and extension sections that is reserved for a future use. So you can see here in a conditional flag, we have number of flags given here: negate flag, zero flag, carry flag, and overflow flag. So here in a control bits, we have a interrupt mask, we have fast interrupt request, we have thumb state, and we have modes. So modes has total 5 number of bits. Using these 5 number of bits, we can select number of modes. So as in a ARM controller or ARM processor, we have 7 modes available for the operation. So in the before slide, you have seen the registers which is in a user mode. User mode is one mode out of 7 modes. Next, the ARM core uses the CPSR to monitor and control internal operation, as I said. So it will be divided into 4 fields: flags, status, extension, and control. And control field contains the processor mode, as we have seen, state and interrupt mask bits. The flag field contains the condition flag. The ARM processor cores have extra bits allocated, which is not shown in this CPSR. So that is a J bit. What is that J bit? Which can be used, which is found in a flag field and is available to Jazzle enable processor, which execute 8-bit instruction. So I'll move to a previous slide. You can see here there is a flag called T state. Fine, thumb state. So we know the ARM works under a ARM is a 32-bit processor, and it can execute a 32-bit instructions at a time. But if we are operating our processor in a thumb state, it is able to execute in a 16-bit mode. And another we have seen a Zazzle enabled processor, that is J mode. So if we enable this J mode, then the processor will be executing a 8-bit instruction. If we are in a ARM state, we will be executing the 32-bit instructions. If we are in a thumb state, it will be executing a 16-bit instruction. If we are in a J state, that is Jazzle enabled processor state, then it will be executing 8-bit instructions. Next, we have processor modes. So each processor mode is either a privileged or non-privileged. So what is meant by privileged? Privileged mode allows full read-write access to CPSR. If in non-privileged mode, it only allows read access to the control field, but still allows read-write access to the conditional flags. Conditional flags can be read or written, but control fields can only be read in a non-privileged mode. But in case of a privileged mode, we can have a full access to read and write to a CPSR. Next slide. There are 7 processor modes in total, 6 privileged modes and 1 non-privileged mode. What do you mean by privileged mode? We have a full access to read and write a CPSR. What is CPSR? Current program status register. And if it is in a if the mode is non-privileged, then we have we are allowed to read the control bits and write the conditional flags. Where are the control bits and conditional flags? These are the control bits and these are conditional flags. Okay, we'll move. As I said, there are 7 processor modes. So one is a user mode. Fine, that's the same user mode register we have seen in a previous slide. The first one, abort. So why abort mode is used? When there is a failed attempt to access a memory. If there is a failed attempt to access a memory, the process will move to abort mode. Next we have fast interrupt request. FIQ is generally shortcut, we call it as a FIQ, fast interrupt request. It corresponds to the interrupt levels available on ARM processor. The third mode, interrupt request, it also corresponding to the same interrupt level available on a ARM interrupt. The fast interrupt request and interrupt request almost gives the same, it almost has the same significance. Next we have supervisor. So supervisor is a mode that the processor is in after reset and is generally the mode that an operating system kernel operates in. Whenever there is a power up, so our system will be moving to supervisor mode. Fine. So in the supervisor mode, operating system kernel was under a control. The processor is under a kernel control. Next, fifth mode we have system is a special version of user mode that allows full read-write access to CPSR. Fine. We have a user mode here. That special version of a user mode is a CPSR, system mode. So the speciality of the system mode is we have full read-write access to CPSR. Next we have undefined mode. So in undefined mode, the processor if the processor encounters an instruction that is undefined or not supported by the implementation, then the processor moves to a undefined mode. When the instruction is undefined or not supported by processor, even though if you try to run that instruction in the process through a processor, then there will be some exceptions. So that exception will move our processor into undefined state, undefined mode. The last one we have a user mode. So user mode is used for programs and application purpose. In the next slide we have banked register. What? Banked registers. So you can see on a screen. So there are number of modes, user and system mode, total 7 modes, user and system mode 2, fast interrupt request, supervisor, undefined and abort. So for each mode we have specialized register dedicated or banked, which are hidden. Whenever the processor moves into that mode, then these register will be having significance. So there are total 37 registers in the register file. Out of those, 20 registers are hidden from a program at different times. These registers are called a banked registers, and it is identified by shading in the diagram. There is a shade on some registers, so those are called a banked register. So as I said, they are available only when the processor is in a particular mode. For example, in abort mode, we have banked register R13 underscore ABT. See here, we have in the abort mode, we have banked register R13 underscore ABT, R14 underscore ABT and CPSR underscore ABT. Now when the processor move from a user or a system mode to a abort mode, R0 to R12 register will be available as it is, but R13, R14 will be replaced by R13 underscore ABT, R14 underscore ABT. You can see in this diagram, we can see here in the different mode, so it will be replaced by this kind of registers. So that means when the mode changes from a user to fast interrupt request, user mode to FIQ mode, the R8 is replaced by R8 underscore FIQ, R9 is replaced by R9 underscore FIQ, R10 is replaced by R10 underscore FIQ, and so on. If the processor moves from one state to undefined state, then R13 is replaced by R13 underscore undef, R14 is replaced by R14 underscore undef. So this is what happens here. I said the processor mode will change from one mode to another. So there should be some reason to change from one mode to another. So because of some exceptions and interrupts, the mode change will happen. We'll see those reasons in the next slide. So the following exceptions and interrupts cause the user mode change. What are those? The reset may change the mode. The interrupt request will change the mode. The fast interrupt request will change the mode. Software interrupts, data abort, prefetch abort, and undefined instructions. So these are the reasons to change from one mode to another mode. So these are the exception and interrupts to change from one mode to another. Fine. The next slide. So changing mode on an exception. So this we have already seen. When there is a change in the mode, the exchange or replacement of register will happen. Fine. Next slide. Subprocessor modes. The same processor modes. We have seen 7 processor modes. Those are abort, FIQ, IQ, supervisor, system, undefined, and user. So these modes abbreviations are given here. For abort we have a ABT, fast interrupt request we have a FIQ, interrupt request we have IRQ, supervisor will be abbreviated as SVC, system SYS, undefined UND, and for a user mode it is USR. So out of these 7 processor modes, these 6 modes are a privileged mode and only a user mode is a unprivileged mode. So what was the privileged and unprivileged mode? We'll move to previous slide. So privileged mode is full read-write access to CPSR. Unprivileged mode is for control field only read, and for conditional flags and read-write access it will be there. That was unprivileged mode. Fine. Now we have some bits, 5 bits combinations are here. So you can see here 0, 1, 2, 3, 4. Fine. So 1, 0, 1, 1, 1 means abort. So where these bits will be? These bits will be in a CPSR. We'll move to a CPSR slide. You can see here 0 to 4. There is a mode field here, isn't it? So mode field is a processor mode. If in this structure, if we get 1, 0, 1, 1, 1, then processor will move to abort mode. If we move 1, 1, 1, 1, 1, 1, it will be moved to system mode. If you have a 1, 0, 0, 0, 0, then processor will be operating in user mode. We have a next slide, conditional flags in a CPSR. As I said, the Q for overflow, that is saturation, we also call it as, you can see here. So it will be set, this Q flag will be set when the result causes an overflow or a saturation. Fine. V is a overflow, the result causes signed overflow. It will be set when the result causes signed overflow. So we have a carry C, it will be set when the result causes an unsigned carry. We have a Z flag, the flag name is 0. So when the Z flag will set, it will be set when the result is 0, frequently used to indicate equality. Fine. Next, the flag N, the N stands for negative. So bit, it will be set when the bit 31 of the result is a binary 1. When the MSB is a binary 1, then that means there is a negative number, then automatically this flag will set. We will stop this session here and will continue in the next class. Thank you.